Just det, när vi börjar med tillståndslistor, de här kan jag inte vara en bättre då.
So, let's start. Jenny here, I think you've all seen her better. Anyway, she took her PhD in my department, Miso here in the Department of Metrology, but she's from oceanography. And we'll see that. 3 years ago. Okay. And since then she's been a postdoc in Italy. We have seen here before. Well, I'm not trying to
It's the National Institute of Geophysics and Volcanology.
And also oceanography, in fact.
Yeah, in the office in Bologna where we do operational oceanography.
And so she has been working with data simulation in oceanography in a model of an ocean, and it's really co-work here with Sylvian, who has already spoken. So although they are in different organizations, they're in fact sitting in the same place and working together. Please, Lynn.
Thanks. So I'm going to present to you the outcome of let's say my main work that during my postdoc. It was actually accepted for publication 2 weeks ago, so I thought it could be nice to show you all some things, and I hope I will be able to explain what we did. If you have any questions, feel free to interrupt me. So we have done some experiments on assimilating Lagrangian data in numerical ocean model. And for this we have been using trajectories from Argo floats. I will give you more details about their characteristics later. But basically there are floats that drift on 350 meters depth, which is the typical depth of the Levantine in the intermediate waters, which are crucial for the overturning in the Mediterranean Sea. And assimilating this data, we hope to improve the trajectory forecasts and the velocity fields in general, and that could be useful because we use these forecasts for different applications like oil spill, cleaning up oil spill, or searching for lost people, or stuff like that. And then it can be very important to have currents going in the more or less right direction. And the Mediterranean circulation in the upper part of the ocean is very characterized by mesoscale motions, so modeling this is not very easy. It's eddies that get shifted a little bit to the north, south, or whatever can completely change the direction of the trajectory.
Degree is 700 kilometers roughly, right? So it's
yes.
Altogether some 700 by 700.
Oh, this isn't the domain. This is just a snapshot to show a bit of the typical circulation. So just to say a few words about the Mediterranean forecasting system. Serjan has maybe not really gone through these talks. Anyways, this is a system that has been operational since '99. It consists of a few parts: the ocean circulation model, which is based in this study on the OPA code with a closed boundary in the Atlantic Sea. At present, the official system is a NEMO version, which has which is nested in a global model, right? So it's not a closed box anymore. But this is still, these experiments are done with the old system, that's it. And so the code was developed by Marek in '98, and it has been modified and implemented for the Mediterranean Sea by Tonani and the group at our institution. So this is just a sketch of the daily cycle. So the model is forced by, has some atmospheric forcing and initial conditions, produces a forecast. In these experiments, I've been using 1-day forecasts only, but operationally it produces 10-day forecasts every day. And okay, so you produce the forecast, then ocean VAR, the ocean 3D VAR scheme runs, assimilates independent observations, And this is then used to correct the initial conditions for the next day's forecast. And here I have been using two kinds of diagnostics to check the quality of my experiments. So it's misfits, calculated between the background field and the observations at this point, and then the difference between the analysis and the observations after. And this is not really an independent check anymore because we have already assimilated those observations, so we would expect that the difference between this estimate and is smaller than any that we include. But it could still be interesting to look at this difference between the analysis and the observations because it gives you a measure of how the model converges towards the observed state. So apart from these trajectories, we also assimilate satellite data and other in situ data, temperature and salinity profiles. I will show you later. So this is the bathymetry of the model. It shows also the model domain. It has 1/16 horizontal resolution. It's about 7 kilometers. 72 vertical levels that are unevenly spaced with higher resolution in the surface and more coarse close to the bottom. What else? In the boundary here we relax to climatology. And we force the model with 6-hour ECMWF atmospheric. This is a list of the observations that are being assimilated. So at this point in operations, we assimilate satellite sea level anomalies, satellite SST, that is actually done by nudging, not 3D bar. And we assimilate also profiles of temperature and salinity from both city expertise and RV flow. So now to this I have also added trajectories. So the experiment I did was over a three-year period. Van Sam, who is one of the co-authors, he basically implemented this assimilation routine and made some preliminary tests for a shorter period, 3 months, using only 4 floats up in here in this region. So now I made a more large-scale test using all float data in the entire Mediterranean Sea for 3 years, and we also made some minor modifications of the code. For example, some constraint that we won't use data that has been floating in areas that are more shallow than 400 meters, because there's the risk that the float has gotten stuck to bottom and then the trajectory wouldn't be representative of the real ocean flow, but something else.
How many floats?
Every year there's about 700 coordinates, so about 2 floats per day, more or less, that communicate with the satellite. And you can see that the coverage is, well, so these are all the positions for 3 years, but they are pretty evenly distributed over the basin for the entire period.
So those are individual or data from. So is every dot one float or one
position?
One position.
So I mean, so here it's clear that these are all the same floats. But I couldn't tell. I mean, which is.
So how many different floats do you have over there?
I think they're about. I think I'll show you later, actually, but more or less like 20. It differs because someday they add more, and then someone disappear or break.
It's not in the Adriatic.
No, it's very shallow. I think they have Yeah, they have added some. But the Adriatic Sea is like our Baltic. It's very shallow, so since these go to 350 meters, these kinds of flow, I don't think they have deployed many there. So this is just a very simple sketch of the Argo cycle. So if you say that this is the initial position, it communicates by the satellite Argos system, tells the satellite where it is, and then it dives down to 350 meters and rests there for more or less 4.5 days.
How long time does it take to dive?
I think a few hours. Sorry?
It's 2 minutes.
Oh,
5
okay.
minutes, 2 minutes.
Yeah.
Maximum. So it's very good for those down.
So it's an hour?
No, I think it's minutes.
Oh, minutes?
Yes, maybe 20 minutes most. It just sinks down to the
Yeah, it's very fast. It's very short.
350 meters sinks.
So that is negligible, the distance in the drift during those diving minutes?
Yes, we see.
In this study, we haven't listed that. But I mean, there is an error
Yeah,
related to it, but we have kind of included it in other errors, which is related to the positioning of the floor.
And how long time does it stay at the surface?
Until it has communicated, 6 hours, more or less. With the new iridium floats, it will be a lot less. I think 2 hours, maybe, or even less.
Because it doesn't have a GPS, is it? Just
Yeah, it has to do with something with the positioning. It has maybe it calculates faster its position. But the iridium floats, I think they started to use them last year. They're kind of new. So these are not those.
And the 350 meters, that's something you can easily change?
It's pre-programmed. So
The new floats have a possibility, they have two-way communication, so you can also change the depth if you see that it's lifting on the bottom, extending on the bottom or something.
You can send something to
Yes, you can also change the profile in a different way.
these old ones, because once at the workshop they showed us they had a float in the classroom and they just plugged in a cable and the other one to the computer and they just programmed it, telling you should go to this depth for a certain period and then come back and whatever, and then we do it. So I think these are, let's say, hard-coded. If you once they're in, you can't communicate. But maybe with these new ones, you can also steer them. So anyways, they dive down to this depth where they drift along with the currents for 4.5 days. And when this time has passed, it goes down to 700 meters. And every 10 cycle, it dives to 2,000 meters. And then it makes a profile going up towards the surface, where it measures temperature, salinity. And that's the data that we have been assimilating operationally earlier. But now we're adding also these positions before and after the cycle, let's see. Yes.
Now, just a technical question. In the first map you showed, I thought that several of the floats, these little worms, were in positions where it wasn't so deep. What happens if it tries to dive to 2,000 and it's only, say, 1,500? Does it stay on the bottom and then go up? Or?
I don't really know.
That's because it slowly goes down and then just stays on the bottom.
Okay.
Mm. Some of you have seen these equations before you do data simulation. I'll just go through kind of fast. So the ocean wire simulation scheme is based on basically it minimizes this cost function where we have where x is the state vector and xp is the background state vector, and this is the nonlinear observational operator, which interpolates the model data on the observed grid, right? And this is the observational vector. So this allows comparisons between the model data and the observation space. And in order to, and B and R are the background and the observational covariance, observational covariance matrices. And I will tell you a bit more about this. So in order to minimize this, the equation is linearized. And where we have the model increments here, and this is just a linearized version of the observational operator, and this D is the misfit variable. It contains all the differences between the background state and the observations. So this equation is minimized by iterations, and the gradient of J is also calculated by adjoint operators. So for each linear operator, there's an adjoint which calculates backwards. So these increments are written in terms of a control vector and a matrix like this, where V is constructed as the background error covariance matrix, and it's constructed like this to make sure that it can be inversed, which is necessary. And since it's very, very huge, it's necessary to put it to pieces. So it has been modeled as a sequence of linear operators, where this BV is the vertical error covariance matrix, which interpolates the corrections in the vertical using EOFs. For the Mediterranean, we have 20 different EOFs, depending on where in the basin it's low, depending on where in the Mediterranean you are. Since different regions have very different dynamics, it's necessary to use many, many different. And there is also a seasonal. There are 4 different EOFs for each region: summer, winter, autumn, and spring. And when you have interpolated the corrections in vertical, you need to also give them a full 3D field, so they are being interpolated in the horizontal also by this VH, which basically spreads the correction using a Gaussian function. And then we have the V eta, which contains the error covariance for the sea level corrections. And we have the VUV, which contains the geostrophic velocity correlations. And this is where the corrections due to the trajectory assimilation, they enter in this operator here. And then finally there is VD, which is a divergence damping operator, which makes sure that we will have basically velocities towards perpendicular to the coast, so to remove spurious behaviors close to the coastline. And so basically the corrections on the field due to trajectory data could possibly have an influence on the temperature and the salinity and the sea level fields because they're connected somehow by these operators.
That's the question.
Yes.
I mean, you have covariance for the sea level corrections, and then you have the geostrophic velocity area corrections, and in some sense they are linked. So
Barotropic, there's a barotropic model which links them.
okay.
from the Argo floats we have only positions, and in order to correct the velocity fields we needed to implement the trajectory model in the observational operator. And this work was basically done by nilsson already. So it's not completely straightforward to do this, because we have a model which represents velocity in a Eulerian reference, frame of reference, and the observations on the other hand are Lagrangian. So in order to just compare them to each other, it's necessary to do some interpolation. So I'll try to explain. So the drift of the float can be described as the change of the float's position, but that depends not only on time but also on the position where it's at. So it's a nonlinear equation. And so as I said, the Lagrangian velocity can be described as the Eulerian using this, we have used the bilinear interpolator. So that on this C grid, for example, we have the Eulerian Eulerian velocity here on these positions, but maybe we have at a certain instant a Lagrangian velocity here, so it's necessary to convert. So basically what we say is that
But don't you use the meridianal velocity differences in 4 points?
yes,
And you in 4 points?
yes, like
But they're
this.
not exactly
I
the
just-
grids which are different.
Yes.
So what is the spatial resolution along the trajectory? Does it only say it's starting and
We
final point, or is it
used every 6 hours, so 20 segments from start to end, because we have saved 6-hour velocity fields from the model, but I mean that you can change also.
So how does that compare to the grid size? Do you get like mostly several positions within each grid cell, or
Yes, sometimes. It depends, I mean, on the dynamics, if there are fast currents that
Yeah,
usually,
sure, but-
so, yes. So basically, now I will just show you for one integration, this equation, using this expression instead of the Lagrangian velocity. So here we see the initial position and the final position being calculated due to the velocity field in this period. So this is a pretty standard way of calculating the trajectories. And in order to implement this in 3D, we needed to do a tangent linear approximation to this model so that we could retrieve the velocity field increments. Basically, the result is this, if you just apply this approximation, where you can express the Lagrangian velocity as this bilinear interpolator in a certain, in the background position, and the derivative of the Eulerian velocity with us to the position as the derivative of this one at a certain position and time of the background field times the velocity in the position of the background. Yeah, okay, so basically this correction then enter here as it is. So I did 2 experiments, let's say one controlled run where I made a mistake, it should be profiles here. Anyway, so I simulated the sea level anomalies, temperature profiles, and the Argo temperature and salinity profiles, not trajectories. And then in the other one, same thing, and also the Argo flow positions. these are some statistical results, so I will just show you this sketch how to interpret this. So if we have an initial float position here, this is horizontal, in the horizontal plane. So the observed float maybe has a certain trajectory to this final position. While the experiment where we did not do anything, there the trajectory ended up here. So our kind of hope is that when we assimilate, the forecast will be slightly closer to the observation, and then that finally the analysis should be even closer. So I have calculated the misfit, the RMS misfits of these positions. So the black line here is the distance between this and this. And the red line is the distance between this and this. And the last green one is the distance between the observation and the analysis. So we can see that we do slightly better assimilating. The red line is almost, the red line is below the black. In percentage, in relative percentage, we're doing 15% better forecasts when we assimilate. And the analysis.
Could you say again, what is
Sorry?
the difference between the red and black?
It's basically the misfits with and without trajectory
What's the
assimilation.
between
The observed and the forecasted position. So we make a 5-day forecast and we compare where it ends up, how close.
The B term that you have in the linearization, the difference between the trajectory and the observations. So, is the second line there?
Sorry.
In the B term,
Yeah.
that you said that there was, those were the misfits for the linearized version. So that is going to be the float observations and the trajectory. Yeah? Did you know, if
Like
we
which
go
B?
back to the question
Yes, sorry.
before, that here, next, it's a D, sorry, it's not a
D. Oh, yes,
Sorry.
yes, yes, yes.
The D that is over there,
Yes, yes.
that is the difference between the trajectory and the observation. So do we put that in
Yeah, the forecast. Yes.
Yeah.
Sorry, I was thinking about the
No, but
graphical
yeah,
areas
it's
matrix.
very good. It's less, never trying to have that before.
And the only thing, I mean, is the previous, what you're really using as the misfit here is the previous forecast compared with the observations today.
The only, let's say, the only difference between these two is that I have assimilated in one, but in that, when I compare, the present day observation has not yet entered. So, let's say the difference is the initial conditions. Because, well, I mean, the experiment where you assimilate accumulates corrections in itself, but this is still an independent check because the observation I compared to has not yet been assimilated. So the improvement is due to the change in initial conditions due to previous assimilation.
And you're just comparing the position.
Yes, just the distance between, like really just this, checking how far they are from each other.
But the data of the float is used twice. Or maybe I'm confused. With the control, you use the profile, and then for the trajectories,
I used to, in the control, I used the profile, but not the trajectories. But I calculate the forecasts anyway, so I can compare with
the
them.
trajectory and the from the profile.
Yes. Kind of. So the trajectory between the initial and final positions from each cycle. So I mean, we calculate trajectories even if we don't assimilate data, just to have a comparison. Okay, so anyway, so you can see that when we assimilate, the forecast gets slightly better, and that the quality of the analysis is very high. It's about 7 kilometers, so it manages to converge to a certain point that the observed and the analyzed position are in the same grid box, basically. because the horizontal resolution is about 7 kilometers also.
What's the typical traveling distance forecast?
The typical what?
How long time? How far is it traveling? I mean, just to compare.
In this, maybe
This
it
time period.
could go maybe 50 kilometers. I think or so.
It's about, let's say, 20 centimeters per second. Those the tanks. So we should calculate what
Yes.
it's about.
I
100
can't
hours.
really remember. I think I thought
Yes,
it's even more.
that's 50 kilometers, maybe less.
Yeah.
But it doesn't mean that the accuracy, relative accuracy, is on the order of 20%.
Mm.
Yes.
That's after 5 days.
This is for the full 3-year.
Yeah, but
Sorry.
the error is after 5 days, right? I mean, when you calculate.
Yeah,
the
yeah.
RCS.
I calculate that.
No.
And then I control the response errors for the other state variables just to make sure that nothing strange happened in the other model fields. When we changed the velocity field, we changed the gradient of the full field. So just to see that I haven't caused huge damage in the other forecast variables. And here we have the sea level anomalies, temperature at the parking depth of the float, and the salinity at the parking depth for the full 3-year period. And we can see that, okay, so the black lines here is the difference between the observation and the forecasted, the observed and the forecasted value. Without the simulation, red is with the simulation. And this is the difference between the observed and analyzed value with and without. So blue is, black and blue are without the simulation of trajectories, and red and green are with, and either way they are basically the same. So you can see there, it's not getting better, it's not getting worse either, it's remaining on the previous levels that weren't that bad either. I mean, if you see the weakness per area for sea level anomalies is around 3.5 centimeters, so it's very, the quality is very high. It's basically
But
on
shouldn't
the-
you expect actually on these other variables also to improve a little? The information of the whole field is
Something,
better.
I mean, something could happen since they're connected to each other. I mean,
I mean, you get
It's really difficult because we are at 350 meters and then it's already below the 10th one in the Mediterranean. It's difficult to connect directly. For example, the surface flow with what is it? Because the currents at the surface are quite different from what they are at 350 meters. So it's we just were worrying that we could make something wrong with other variables. So it was, of course, we were hoping to get something better, but
yeah,
it
maybe
didn't
sea
happen.
level anomalies, but still. And then, I mean, we assimilate huge quantities of satellite SLA data. We have maybe 2 floats per day, so even it's not so likely that it would have a super influence. And then I did some tests just to see how these corrections spread around the simulated position. So this here is the difference between the velocity fields at 365 meters after. So I started the experiment on the 1st of January. So this is almost 4 weeks later. I chose that date because I had many bruises. And all these dots showed all the previous positions from the 1st to the 24th of January. We can see that the differences between the 2 experiments on that day is clearly located around these previously assimilated Argo flows. So there is some kind of that. So you can see an impact in the close region to the floats. And then I checked the difference from one day to another between the 2 different fields. So from the 25th to the 22nd, and in that period we had only coordinates from 2 floats here, and we can see that the largest differences here are also close to where we assimilated. But we can also see still some sign of previous assimilation where we had date also before. Like you can't see that much, but there is something. So there is some kind of memory of the corrections that we have made previously. We estimate that at least on the order of the Argo cycle, like 5 days. So when we add this information to the system, it doesn't go lost immediately. And then I made a zoom in here in the Algerian current to see what local impacts it could have on the velocity fields with the assimilation. So this is the control. So here I haven't assimilated anything, and here on the other hand I have. And these are the previous day's observations. This is the observation on the 25th that I have not yet assimilated because it's in the next step, let's say. And the red line here is the prediction of the float for this period, let's say. So we can see that without assimilation it's pretty wrong, like 90 degrees in the wrong direction. And when we assimilate, so that it has different initial conditions, it's still not that good, but a little bit better. This northward flow is caused by this eddy here, which probably isn't in the right place, because you can see clearly that the observation go across this field. Here it is slightly diminished. And here, on the other hand, it's the velocity field the day after, so it's the day after we have assimilated this. As you know,
To me it seems like this one thing, just this observation, almost wiped out that eddy.
Yeah. Yeah. It removed, or I mean,
of course, something remains, but much weaker. So
yeah.
the eddy is mostly vanished. And that's because this single observation.
Yeah. And then afterwards, when it has been assimilated, you can see that the flow structure completely changed, and now it's more following the observations. This is a very dynamic area with the Algerian current meanders. So I mean, this one example, you might have eddies. Maybe it's not really like wrong that there is an eddy, but it shouldn't be exactly here. Maybe it should have been more up in some other direction. So the assimilation manages to shift the currents.
And they're very small, these are the small, I think.
Yes, yes.
The radius may be 15 kilometers.
So it's only partially resolved.
And
But
that is
small structures.
really the problem with the ocean. The lost radius is too small. You need a lot of those.
You mean that it adjusts back? In the atmosphere we talk about when you circulate, then it's a geostrophic adjustment going on.
Yes.
But what happens here if you insert only a small wind or a small stream?
Yeah.
Is it so that it goes back? It just disappears as some waves, or
Well, that is another question.
or is it not a relevant question in your way?
Yes, it is.
Yeah. Because you have some damping, you said. You have some divergent damping.
Yeah, the velocities are almost geostrophic.
Ah.
So because
So
the
you have
velocities are much smaller
geostrophic
than
increments in the salinity and the temperature.
yes, we balance.
You balance completely. Okay. So then it should be preserved.
But still, the roster radius is small, so you need to take Berlusconi's entire budget to... can you do that sort of theoretical calculation? How many Argus flows do you need in order to really filled with enough. Because on these corrections you only have like spots like this.
Yes, for temperature and salinity, which have a much larger correlation scales than the velocity, they calculate, I think, at least 50. That was Wolfgang did the calculation. Wolfgang Gruppen.
Yeah, he used to work with me.
Yes. So he made these calculations, but then for this it would be much larger than the number.
Yeah, this is the so small. So out of curiosity, I made a section here to see how the trajectory assimilation influenced the velocity and the temperature and the salinity in this at this instant at this point. So this is the zonal velocity fields. So it's the same day, same models. And this is the, let's say, the last, this is the position in the meridional of the float before it surfaced. And you can see there is a slight shift of this core to the north. Here below I have just calculated the difference between the two fields, so let's see, maybe numbers, there is 3 centimeter per second difference, 5. So close here where we have, where the core has been shifted northward, there's a difference of almost 6 centimeter per second. And just to get a feeling for what that actually means in the terms of transport, I made an estimate, so I calculated the area here where it has moved away from. It's about 0.2 degrees and maybe 200 meters, and gave that a local shift of velocity of that magnitude would mean like a difference of almost 10% of the total transport in the current. So, I mean, maybe it doesn't look that much if it's just slightly moved. It has the same structure, but in a single point it could make a huge difference of but then on the other hand, the current is probably moving a lot, so it could be at that instance there's a 10% difference in the transport, what would be expected. Do you understand what I mean? So it's, I mean, so the impact is not that small. I mean, the assimilation actually changes the flow structure of a lot of water. And this is the corresponding temperature fields. You can see that, so this is the last position of the float. And one kind of, to me, striking thing is that this entire blob disappeared. And you can also see it here in the differences. So there's a 0.5 degrees Celsius that changed. And I was kind of, who knows if it made it better or worse, I will show you later. And you can also see that the entire gradient of the temperature changed due to this shift of the core of the current, making the water about 0.2 degrees cooler in the surface waters. And same thing for the salinity fields. You can see that the gradient is slightly shifted, and that the surface water got a little bit fresher close to the coast. So the buoyancy properties in the region was changed due to the changes in the plastic fields. So then I made a comparison of so in the end of the cycle, the float makes a profile of temperature and salinity. So I made a comparison of the model data and the observation in this point, just to see if like these changes in structure are making it better or worse. For example, also it made me curious whether this is better or this is better, for example. Because
but this profile is already assimilated.
The profile is assimilated, But
In both cases.
in both
Control there.
cases. But so it's only because of the trajectories that this happened. I mean,
But I mean, you're comparing the profile with output that has already used the profile.
no, it's calculated before assimilation. I'll show you. So it's so I have so in these two top figures, it's only a comparison between that measured profile and the temperature and the modeled data, let's say, in that profile. And same thing here, the black line is the misfit between the forecasted without trajectory assimilation and the observation, and the red is with assimilation. While so this is before assimilation of anything, and this is after analysis versus observations. I realize it's kind of confusing, but I mean, when I say before assimilation, I mean before everything, but in the red one, trajectories were also included. See? So we can see basically that both for temperature and salinity, we actually do worse in this case, because the difference is the RMS is larger. So the changes of the structure of temperature and salinity was not that successful in this occasion, even though the velocity field got better. But then I thought, well, in the previous long time, the 3-year plot, I couldn't see that big of a difference. But that was actually done for data on this level, so I thought maybe I just didn't see it, because I should have maybe looked at what happens up in the top part of the ocean. So then I calculated the 3-year mean values for same thing, so using all floats for the entire period. And then there's no difference anymore between, so we see that the red and black are basically on top of each other, and the green and blue. So the quality of the forecasts and the analysis on the long run is maintained. So okay, so we made worse this time, but if the long-term mean is the same, it means that at some occasion we also do better, because it wouldn't be possible. But
How that plot, the two plots on the bottom look like, instead of plotting the mean, plot the standard deviation, or something like that, because maybe you would see there are some places where you have better performance than others, or you just plot the percentage of the whole values.
I just plotted the average of all the mean square errors.
Because maybe you see canceling effects.
So anyways, so I found these results like comforting, because then meant, well, okay, so we made worse one time, but on the long run it didn't create like a disaster. And this is, sorry?
But also I think in deeper layers, the temperature and salinity errors are close to the observational errors.
Yes,
So
it's
it's
in
even a
fact.
bit more difficult to get better than,
Yeah, it's already at the limit of what we can
and also for
do.
SLA. It's,
Yes,
it's
yes,
also-
yes. Yes, exactly. SLA, as I said, is already on 3 centimeters. It's on the satellite observational layer is 4, 3, I think 5. I don't know. So we're really at the limit. You can't really even say that much about anything of this. Because I think the observational layer is like 0 points. I don't remember. Something 0 points.
Yes, it's instrumental, but also.
Yeah, yeah. And the reason also why let's say we made worse here is a really dynamically active area, and maybe the UFs that are mean values for a certain region, they can't represent everything if it's very like active. So it could happen that at this certain point it wasn't really well represented by the error experience. So, okay, so this is basically my last slide. we made some validation also. I compared the velocity fields to drifters data. It's on the surface, but since I saw in the other analysis that the trajectory assimilation also changes the surface currents, I would like to know if in which way, if it's making it sometimes to measure the quality, I mean, of the surface currents after assimilating trajectory data at 350 meters depth. So I found that this instant drifter located pretty close to an Argo float here. It's in the Mesa-Matru gyre. It's located here in the middle of the Levantine. So these two top figures show the velocity field at 15 meters depth, which would be representative of the drifting, the draw, what's it called, the draw of the drifter. And this is at 365 meters depth as before, so it's the depth of where the Argo float drifts. And here we have no trajectory assimilation, and here we do. So this is the predicted trajectory between the 11th of December until the 16th. Without assimilation, it's doing pretty well. It's going towards the observation. And after, or on the other hand, with the experiment where we did assimilate, you can see that this entire gyre has changed a bit its form. The forecast is still here I would say it's almost worse, but still it's going pretty in the right direction, where this black one is the analyzed trajectory, so it's the, let's say, the backward calculator, so this one follows nicely the path between the two positions. So we can see at this depth, clearly, one way or another, it has changed the gyre structure. And here I have just put the positions once more to remember where they were in comparison to the drifter. And these drifters give data every day. And I have put the positions from the 16th, so from the day of this forecast, and for the following 6 days.
Is the drifter somehow assimilated?
No, it's completely independent. It's just some data to give an estimate of the surface currents that I used. So this big star is the position when this forecast. So if we imagine that the surface currents for the next few days will kind of be similar to that day, see that for the first period, well, it's going kind of in the same direction, but here we have a strong northward current that is not the drifter is not going that direction, it's going perpendicular to it. But on the other hand, when we have simulated the Argo float data, we see that it's still going kind of in the same direction here in the beginning, and it keeps going. The drifter position follow the modeled field better, I mean, in this case, compared to here. So this part of the flow has been shifted northward. Here you can see because the plot is cut, but it was just shifted up here instead. So you can see that the assimilation of the Argo float positions at depth has managed to shift the full 3D field of at least upwards in the water column. So.
Could you have done trajectory prediction simulation of the drifter and see where it should have gone if it would have been the first velocity field and the second velocity field? So kind of use the same approach as you did below, but on the drifter to evaluate the effect.
To go backwards, like the simulated drifter will not Argo and check the...
No, but kind of on the upper left of the velocity field, up left.
calculate the misfit with the drifter like you did with the brokers.
yes. In fact, I could have, but I didn't.
Yeah.
Because I didn't. When I did the model experiments, I didn't have the data. I found them later, so then I used it. But I could have. I mean, actually now we're working on implementing surface drifter assimilation also, so it could have been very possible. I mean.
Did you look at more drifters? This is one case. Here it is ruled.
This was actually, in this period, I didn't have much drifter data because most drifters I have after this experimental period, and this was the case when we were, I had a drifter pretty close to, because I mean, it was, I was looking by chance to find a drifter that was close to an Argo at that same location.
And this is the only one.
This was the first one I found, and it looked kind of good, so I took it.
And it must have an impact this way, so if you don't include the surface drifters, you can get data every hour and continuously.
The drifters.
Yes.
So we have done some preliminary tests on that, and it seems like it could work. It's kind of a work in progress. I mean, technically, you could use basically the same implementation, just change some parameters. There's some differences. Just surface layer is kind of different. It's much more variable and maybe it could be more difficult to make the surface layer converge towards observations because there is more action going on. Maybe if the differences are really large and you force the surface layer to converge towards the observations.
Because it's directly correlated to the wind.
There are also inertial oscillations and stuff that we are at the Argo depth. There's not so much. It's almost already that's disappeared from the lost field. So there's I think there's more the surface layer is more troublesome. So let me see. So this is basically just what I said.
Okay, thank you. More questions? We have several questions already.
I was wondering about Gibraltar. Does that have a particular effect? Is it difficult to model, or is it good to model, or is there anything in particular happening there because it's flow? So
I think it's actually it's quite difficult to model because as a first approximation, the flow is very simple. There is an inflow of Atlantic water to the Mediterranean at the surface and the outflow of the Mediterranean at the bottom. But then there is a very strong action of tides because there is a shallow depth and there is lots of mixing. So to simulate that, you need a very high resolution, which we don't have. So we parameterize somehow artificially the mixing instead of, because we don't have tides also.
In the model.
The process, yes, also the measurements there are very difficult to make because the currents are so strong and there is this internal wave breaking and also the shift from one direction to the other with very strong velocities. And there are very few observations in that area because that's usually people lose instruments, so they don't want to put anything there.
Isn't it because they have the submarines are just lined on each other there?
Yes.
You can't measure anything. I mean, it is military.
Yes, probably. That's fine.
But more seriously, you say you don't have any tides. I mean, basically you can have tides in two ways, I guess. One is to relax to some sort of observations,
yes.
and the other one is to have a tidal potential. But maybe
Yes,
most important
we
is to
still
have a
didn't
good.
implement that, but still the horizontal resolution is too small to simulate these processes that are very local. There are some small seals, rather than small mountains that are very narrow, and the model with the 6 kilometers resolution.
But you running Nemo, you can use a glyph.
Yes,
It's
that
nested.
would be a possibility.
But in the model that you talked about, you simply don't have Gibraltar.
Oh, yes.
Oh, but you said this was the old version. Where you had
Yeah,
Gibraltar.
no, we have there's the Atlantic, there's a box in the Atlantic in the new Nemo model we're nested into the global model.
Yeah. And there you have this, but still in this case, in the new version, we have this Atlantic box. You parameterize the flow through the strait.
Yes, in both cases.
Okay.
Yes.
Could I make a comment on the Mediterranean tides? It's a well-known fact that they are rather insignificant. This surprised Julius Caesar when he invaded England, because when his army got across, they camped on the beach at Dover and were very surprised by the tide. And actually the same thing happened when Alexander the Great marched towards India. They camped where the Indus goes into the Indian Ocean, and they had the same unpleasant experience.
They were not used to it.
No, exactly.
Sure, but the tides are still important in Gibraltar.
So any more questions? Comments? Okay.
So next talk then is tomorrow morning. I think that was Nils speaking tomorrow.
Yeah.
10:30. And if anybody else wants to come for the conference dinner on Wednesday, then they should please pay to Anne within the next 10 minutes. And Anne is and Nils, are you coming for the dinner next Wednesday? Are you coming for the dinner next Wednesday?
It seems that I need to go home to students in Oslo. They require me to come back.
On Wednesday?
Yeah.
All right.
So I go back on Wednesday.
Okay, good. Right, that's it then.
Jag hade några biljoner vad som är på dem.
Ja, men alltså, det är bara mer och mer och mer.
Fylla så att jag... Ja, men det borde